Hello and welcome to PCB Chat, where we talk with experts across the printed circuit design, manufacturing, and electronic supply chain fields. I'm Mike Buteau, president of the PCEA. My guest today is Claire Wemp, Ph.D., a thermal applications engineer at DuPont. We're going to talk about thermal interface materials and women in electronics. And as I say that out loud, it sounds a bit like a non sequitur, but I think both are important and interesting topics. So with that, Claire, welcome. Hello. Glad to have you on PCB Chat.
Hi. Thanks, Mike. Happy to join.
I mentioned thermal interface materials, but for today, we're going to talk about TIM1 materials. And it might be confusing for those who don't know about the TIM1 and TIM2 classifications. Do you want to take a moment to explain the difference?
Yeah, absolutely, Mike. So TIM materials or thermal interface materials are basically, you can think of it like a soft or pliable material that is placed between two hard materials to help assist with heat flow, going from a heat source out to some sort of heat sink. And so if we think about a typical computer chip, maybe a GPU on your laptop, you've got your PCB board, you have some sort of silicon wafer that's attached on, maybe a flip chip design, and then usually there's some sort of lid that fits over top of that. And at most, if you're the kind of person that tinkers around with computers, you're going to be seeing that lid. You might pop off the heat sink, the finned device of some sort. You're going to see that lid there. And you might actually see a TIM material between the lid and the heat sink itself. But when we say TIM1, we are actually referring to thermal interface material that is below the lid. So it's the TIM material that goes between, if it's a flip chip, between the back side of the die, so it's actually touching the silicon, and the lid, which is usually some sort of metal material. So it's kind of the first line of defense from the heat source out to that lid material.
There's obviously a trend toward removing heat from electronics by the means of lower power devices. I think of Intel's Atom line of processors, for example, or AMD has the new Zen 4 chips. So can you tell us a little bit more about where TIMs fit in? You know, if device manufacturers are trying to take care of some of that simply by introducing lower power devices, what are some of the other hurdles that you have to go through, or reasons why you might use a TIM in order to get some of that heat transfer or dissipation?
Yeah, that's a great question. So lower power devices, or just the power in general coming from the device, is really only one factor that you would use maybe in selecting the type of TIM. Or for that matter, as an application engineer, one of my main roles is qualifying TIM materials and better understanding whether or not that particular sample will actually work in a given application. So heat flow or heat flux is one of those. Another factor is the size of the chip itself. Larger die sizes will result in more warpage. There's a CTE mismatch, or a coefficient of thermal expansion mismatch, just by the innate property of the material between that silicon wafer and the lid, which means that your TIM1 material is going to be experiencing the stress and the strain of any kind of flexing or mismatch between those as the temperature changes, maybe through power cycling or temperature cycling. So a larger size of a chip, particularly the corners and the edges, is going to be experiencing a lot more stress and strain. So you might need to choose, for example, a TIM1 material that has a softer, maybe lower modulus, to be able to accommodate and move with that without actually delaminating from either the wafer or the lid. In addition, you might want a TIM that has more adhesive properties, that's going to adhere better to the lid or to the chip to accommodate that. So die size, in addition to heat flow, is part of that. Not lastly, but the last one I'm thinking off the top of my head is the temperature. What are the extremes that this particular material is going to be experienced, both on the cold side and on the hot side? And this will depend on the application. So generally speaking, for reliability testing to qualify a TIM material in like more of a consumer electronics application, you're going to need to pass reliability thermal cycling that will go from negative 40 degrees C up to about 125 degrees C. If it is a chip not going into a consumer electronics, but rather into maybe an automotive application, or computers on wheels, as essentially they're becoming, those chips now have to cycle from -40, sometimes even lower than that, up to 150 degrees C. So rather than 125 degrees C on the high end, now it needs to go to 150. And as it happens with certain types of materials, that variation between 125 and 150, it makes things change in the polymer on a molecular level that could adjust or change the modulus or the adhesive properties. There's a lot of really smart chemists at DuPont that really work to develop formulations that can go from 125 to 150 without maybe experiencing those changes. That's certainly a challenge in the industry now. So understanding what are the temperature extremes and how is my given material responding in its modulus, its adhesive properties, and then of course in its thermal properties.
Meet and learn from leading experts in printed circuit design and manufacturing this year at PCB West, coming September 19 to 22nd to the Santa Clara, California Convention Center. PCB West is the only event to feature experts like Rick Hartley, Lee Ritchie, Susie Webb, and Zach Peterson, all in one place. Join thousands of industry professionals across the 4-day technical conference, which offers more than 120 hours of in-depth training, and meet the more than 100 industry suppliers on hand at the one-day exhibition on September 19th. Register today at pcbwest.com and get in on the action. When we're talking about those temperatures, my understanding is that the TIM1s are mostly silicone-based, correct?
Certainly the ones that are being offered by DuPont are currently silicone-based TIM materials. And that means that they're dispensed in an uncured state, and then they actually go through a curing cycle once they're in the package. That will help to cross-link the material, make sure it's going to be adhering better on either end, and it also slightly increases the modulus just to make it less flowy and stay in place really nicely during those reliability tests.
Let's talk a little bit about the processing. Are they always dispensed, or could you actually apply these to the board, or really, could you apply these in general through any other mean?
It's a great question. Generally speaking, the silicone-based materials that go through a cure are dispensed onto the chip, either in a pattern of some sort, and then the lid is pressed on. And that's an automated process. The types of dispensers vary a little bit depending on the material or depending on the OEM that's manufacturing it. There are a couple exceptions, ones that I'm maybe slightly less familiar with because they come from other companies, but there's some like solder pad materials that would actually be solid in room temperature state. So you place it on in a solid state and then burn it in or melt it in, and that would melt into place. But those are for very niche applications and sometimes don't meet the same kinds of reliability requirements that our polymer TIM applications are used for.
This might be diving a little bit too far into the weeds, but is the nature of these materials, are they thixotropic or are they pseudoplastic?
Oh, if you're talking to a mechanical engineer here, not a chemist. I honestly don't know the answer to that. I know that there are people at DuPont that would, but being someone who works more on the application side rather than the formulation side, I can tell you that they're stretched in their uncured state. When I have tested them or run tests with them, they're gooey, kind of like melted cheese, and stretchy, very good adhesion. And then once they go through the curing process, we like to refer to them as more of a gel material. So they have a little more springiness, a little more elasticity. Certainly, if they're adhered between the two plates that they're ultimately going to go to, they have really nice adhesion as well.
Okay, so this might be more up your alley then. In your experience, who makes the call on TIM use? Are they designed in, or are they added afterwards because testing is showing that there's unacceptable thermal gradients or some other heat problem?
Oh, it varies so widely. So I've been working specifically in this TIM area for about 5 years now, after doing a lot of more academic research in the space. And when I first joined 5 years ago, most of it was kind of what you described there. It's like a back later in development stage where they're like, oh my goodness, the electronics engineers have designed this thing that's producing a ton of heat, and now we have to respond and try to find a thermal interface material that'll meet whatever scenario has been thrown at us. Some of the higher end electronic device manufacturers now are starting to incorporate thermal management earlier on in the design phase, which in my opinion is fantastic because, what it means you can do is rather than having someone come at you and say, well, here's our PCB board, here's the spacing of all of our components, deal with the thermal. You can come back and say, well, gosh, it would be really great if we could separate out the memory and the GPU just a little bit more so that we can have, a more even distribution of heat, or maybe we'll incorporate some heat spreaders or something like that. And there can be more of a conversation back and forth. As I'm sure many of the listeners know, designing, scaling up and manufacturing PCBs is expensive. And it takes a lot of effort to kind of figure out the placement of everything. And so if you don't consider the thermal, oftentimes by the time thermal is incorporated, you've already got a design, you've already done scale up, you put in all of that early capital funding, you don't really want to go back and have to start from ground zero moving things around. So the earlier the better. It varies so much. DuPont works with a lot of different customers, and I think many of them have their own kind of approach to it.
You mentioned heat sinks a moment ago, and I want to kind of just ask, are you seeing TIMs used as a possible replacement for heat sinks, or are they typically going to be used simply because the chip itself, there's no other solution, but the heat sink is still going to be there to resolve some subsequent issues?
So the thermal interface material doesn't act as a heat sink. It's merely the means to get heat from one place to another. If you were to literally stick the heat sink, which is usually metal, directly on top of the lid, you're going to have metal on metal, and that on a micro scale, that has a lot of air gaps. Air is a thermal insulator. You don't want that. So really the TIM is just serving to fill all those little crevices. So no, I don't see the heat sink going away. However, what exactly the heat sink is varies a lot. So historically, you would see finned heat sinks, just metal fins. Sometimes we see pin fins, which are more just like individual rods sticking up, and you have airflow. So if any mechanical engineers out there, their heat transfer classes, it's, convection cooling, just got air blowing over it. And the different kind of controls that we can adjust with that are the temperature of the air, the speed of the air, and that's about it. And it takes a lot more HVAC cooling. If you need to lower the temperature of the air, or if you need to turn the fans higher to blow the air faster, that takes energy. And so sometimes, and it's also just loud. I don't know how recently you've walked through a data center, but oh my goodness. When fans are running at 100% duty cycles or 80% duty cycles, it is loud. So ideally, you want to try to reduce that as much as possible. And people have designed all sorts of cool heat sinks to do this. Now we start seeing heat sinks that have heat pipes incorporated inside of them. So we have these usually copper kind of vertical heat pipes and then horizontal fins, and you still have air blowing over it, but the heat pipes introduce an evaporative cooling component, which is pretty nifty. And so then you sort of have both convection cooling and evaporative cooling happening inside the heat pipe. But in essence, you're still just blowing air over it. When we get to really high end, especially in data center applications, we're starting to see liquid cooling. And so you might have a cold plate with an inlet and an outlet for liquid coming in. And even in many of those cases, you still need to have a thermal interface material because that block of metal that is the cold plate still has to attach somehow to your lid, or in some cases, actually to the die itself. Some designs will actually remove the lid. And in that case, we actually call the thermal interface material a TIM 1.5, kind of the hybrid. Essentially, you got the backside of the die, the TIM 1.5, and then some sort of heat sink sitting on top. But in any case, the heat sink can come in many, many forms. I probably haven't even talked about half of them, but it's a great place for a designer to get creative and also think really critically about the space that you have to operate with.
So in the companies that are really thinking this through, who all is in the room at the outset?
It's going to be a really great cross section of engineers, electrical, mechanical. You could probably have PCB designers in there. Probably got some budget people in there thinking about how much things are going to cost. You might even just have some general designers. As we know, working in the electronics industry, everything gets ripped apart on iFixit or one of these online websites, so you want to make it look pretty from the inside out. Yeah, honestly, that would be my guess. off the top of my head, since I'm never sitting in that room as a supplier of raw materials. But that would be my guess. Is the folks in there are going to range from electrical, mechanical, and design.
Mm-hmm. So let's switch gears for a moment. You've been involved in the Society of Women Engineers since your undergrad days and continued that effort while working on your doctorate. What drove you to get involved?
So when I started my undergrad at Santa Clara University, I was in a class of mechanical engineers, about 90 of us, and I think there were maybe 6, possibly 7 mechanical engineers that were women. In high school, I never really thought too much about the breakdown of gender because most classes were split 50-50, but I'll tell you, it's pretty shocking to walk into one of your morning seminar classes and be one of 2 women in a 100-person class. And it really hit me in a way that I didn't expect. So I did actively seek out ways to engage with other women that were sort of going through the same process as me. A little bit solidarity, a little bit social, and also really working to make sure that future generations were not going to experience that same thing that I had, just being sort of one of the lone wolves in the room. So Society of Women Engineers is an international organization. They have sections that are at the collegiate level. They have sections that are professional sections. I'm now part of the Santa Clara Valley section of the Society of Women Engineers on a professional level. But the undergrad sections just do a fantastic job of engaging and creating a space for young women who are desiring to pursue engineering to really share their joys and their struggles, but also to connect with professionals in the area that have gone through that and sort of seen the other side of it. And so I think it's a fantastic organization. I've been involved, like you said, ever since undergrad, and continuing through grad school and now as a professional member.
Per the National Science Foundation, if we look at all science and engineering degrees, women accounted for half of them in 2018. But if we look a little closer, the NSF goes on to note just 22% of engineering degrees in 2018 were awarded to women, which is up only 4 points in 20 years. Now, the percent of doctoral degrees has almost doubled in that time to about 25%. But if you think about this more broadly, I mean, women aren't just switching to coding either. I want to just point that out. That percentage has actually declined 7 points in 20 years. So I'm going to guess that awareness and recruitment were really big topics of conversations in some of your SWE chapter meetings.
Huge, Mike. Absolutely. So the studies done by Society of Women Engineers, NSF, and then I believe the American Association of University Women, AAUW, has shown that women and young girls typically start self-selecting out of STEM classes whenever they can, or they start telling themselves that I'm bad at it, and that kind of perpetuates a desire not to pursue it between 5th and 7th grade. And if someone starts telling you at that age, well, you're just not good at it, then you're not going to have a desire to do it. And when I read that data, I thought back to my 4th grade teacher who told me the opposite. Who told me you're good at math and had me start doing some advanced stuff with a couple other students. And I mean, I'm sure at the time I didn't think too much of it, but for all I know, that could have been a linchpin that got me excited about it and continuing. So for outreach efforts, that's a big part of SWE. We have SWE Next, which is sort of like a elementary to high school club to try to engage even younger students as much as possible. We would do lots of outreach activities, trying to bring hands-on engineering to students at young schools. And again, not just women, we'll bring these activities to classrooms that are, of all genders. So that's part of it. But one of the things I really want to highlight, I think this is something that often gets overlooked. Many times engineering, when people say, well, what are the key skills that you need to be an engineer? People say, oh, you need to be good at math and science. And that's the conversation ends after that, right? So you could imagine a young girl hearing that and thinking, well, gosh, I don't like my math and science classes, or I'm not good at it. And they'll just figure I won't be a good engineer. And what I like to say to that is that if you're an engineer that's really, really good at math and science, but you have no creativity whatsoever, you're not a good engineer. And so you could be so good at these, but we really need people that are thinking outside the box and thinking creatively. And part of thinking outside the box is having people from different backgrounds that just naturally think differently because they've experienced different things in their life. And that could be gender, it could also be cultural upbringing, it could be socioeconomic status. There's so many different things. One of the stories that I had a design engineer tell me when I was an undergrad is that when they were originally setting the building code standards for kitchens, they set the countertop height to be appropriate height for the average male because all the people sitting on the standards board were men. But at that time, most of the people that cooked in the kitchen every day were women. And so they spent all this time and money and they built all these standards and they started doing testing and they brought women in and the women said, well, gosh, these counters are way too high. And I think it's a very funny kind of practical example, but the reality is that most of the things that engineers design and build are being used by men and women. And so if we don't have a diversity of people sitting at the table, you're going to end up with a counter that's too tall, metaphorically speaking. So I really do feel strongly about getting that pipeline going and trying to remind young girls that creativity is as much a part of it, if not more so, than just being good at math and science. I didn't like physics when I was in high school. And I became a mechanical engineer. So what do you know?
So I love your take on it, Claire. I'm a bit sensitive to this topic as my mom is a retired pediatrician. And when she went to med school, she was the only female in her class. Now, today, med schools are still slightly more male than female, but not by much. So bringing this back to electronics, I totally get the creativity part. And I mean, believe me, I had a panelist at our conference, PCB West, last year, who she's the director of engineering for Collins. And she talked about how kids who play Minecraft and they think in 3D, right? They think in abstract ways. And she felt that the next generation of engineers, the folks who want to train those people should be focused dead center on that group of kids because their brains are already wired that way.
Yep.
Are there specific things, along those lines that we in the industry can do to help encourage this and to help not just educate young people, because I agree with you, it's got to start in elementary school, not just educate them as to what the possibilities are, but then also help them walk through a path and so that they could see where the things that they're doing today might actually translate into, the really cool products of tomorrow.
Oh boy, that's a great question. What are the things that we can do? Well, it really comes down to how are we educating young minds? I don't have children myself, so I'm not really as familiar with what the school system looks like if I were to hop into a classroom right now. But I hear a lot about, teaching to the test and having a lot of these kind of closed formed questions where there is only one answer. And I think that if we want people to start thinking outside the box and being more creative in their approach, we need to give them challenges that have more than one solution. So almost all of the activities that Society of Women Engineers brings into the classroom are these sort of open book options. We give you a bunch of tools and we tell you this is the goal that you're trying to shoot for, but however you want to do it, go ahead and do it. Some of them are even, the simplest thing was one where we give a bunch of paper and tape and twist ties and a few other things, but everyone has exactly the same amount of it and a marble. And we say, you have to start at table height and design some sort of something. We don't even call it a ramp, although most of them end up doing a ramp of some sort, but design something that will allow this marble to travel to the ground as slow as possible. And whoever's marble takes the longest to get from top to bottom, you're the winner. And so people will do like spirals, kind of like a swirly slide of some sort or different things. But every once in a while, you'll get a kid who designs like a pulley lever system. It's just like, wow, you were not taking the easy route. They didn't look at what other people around them were doing. And I just get so excited when I see that. And to me, that maybe it's those folks that are doing Minecraft, essentially Minecraft is just a giant open source, game where you get to do whatever you want to reach your goal. That's exactly the kind of stuff that we can and should be doing more of in schools.
What are some of the things that DuPont is doing to help move the needle in terms of attracting more women to engineering in general and perhaps specifically to electronics?
So I think there's some practical things from the benefit side, and this is not just DuPont, but DuPont is one of the people standing on the board. In fact, DuPont is on the corporate board for SWE, so certainly they help kind of playing a role in any kind of lobbying efforts or different logistical things that SWE is trying to do on a more national level. But as a company, I would say some of the big recruitment tools, and again, bearing in mind they're usually recruiting people in their 20s and 30s, either coming out of undergrad or out of a PhD program. They recently increased their paternity and maternity leave. So if you're someone who's looking for a company and thinking of starting a family, that's kind of a big deal. Not all companies have really generous policies there. Or more importantly, they have a policy, but people might not use it, or the culture doesn't encourage people to use it. And I have absolutely seen both men and women taking full advantage of that at DuPont. And I see that as a really positive thing because it creates a culture of welcome and inclusivity. And when people then come back from maternity or paternity leave, I've seen people get promotions a couple weeks afterwards. There isn't a negative downside to that. And I think that is a cultural thing that probably takes years to build, but DuPont, I believe, has done a really excellent job of that. We have an internal DuPont Women's Network, or DWN, and we bring in external speakers as well as internal speakers talking about different topics that are relevant to women. So that could be, how we can bring our whole selves to the workplace, or creating a culture where we don't feel like we need to hide a certain part of our personality or background when we come to the workplace. I won't go into great detail on that. That might sound really foreign to some people, but I was, really surprised. There's, certain factors of people's culture or personality or whatever that they just never share. And then because of that, they feel like they're hiding something, and that can actually ultimately be detrimental to their presence in the workspace. So that's one thing. We really try to be more open about talking about wage equality and, fighting for promotions and knowing how to promote yourself, how to speak up in a room, which oftentimes can be very male dominated. And so we create spaces to have those conversations. DuPont Women's Network is one of those. Beyond internal workplace organizations, or ERGs, we have been doing work for recruiting externally to try to increase our basically recruitment pool of women engineers. So that includes recruiting at the National Conference for Society of Women Engineers. It includes actually reaching out to not just Society of Women Engineers, but any kind of other chemistry women organizations or clubs on campuses when we do campus recruiting, to make sure that those clubs are advertising to their constituents to come out when we recruit. Yeah, there's a couple different avenues we're going. Those are the ones I'm thinking of off the top of my head, but it's certainly something that is in our thought process as we go through recruitment.
And how would someone in industry get involved in Society of Women Engineers?
Well, you can go onto the Society of Women Engineers website and search to see if there is a section that is near you. If you live near a big city, odds are that there probably is a big section. If you live more rural, that you might have to join virtually. But a lot of the sections right now, we're kind of all slowly transitioning out of the COVID era, and maybe just beginning to offer some more in-person events. My local section has been doing coffee hours roughly once a month, where we choose a local coffee shop and just have a range of couple hours one morning, and people can come out and grab a cup of coffee and chat. And that has actually surprisingly been a really successful avenue just to kind of get people connected. And that would be my first thing is, just start seeking out a local group and go to an event, get involved, meet people. You'd be really surprised. Everyone's so friendly and so eager to help out. Oftentimes we'll get folks, I work in the Bay Area, and we've had some layoffs from a variety of tech companies in the area. So there's been some women in our section that are now seeking new jobs. And so we're having these wonderful conversations about, how do I, update my resume for the first time in 5-10 years, and, making sure that I'm getting a salary that I'm worth, and how do I negotiate that? And, these are all extremely valuable conversations, some of which might be considered taboo in certain circles, but we're kind of trying to break that down and really be transparent about it amongst the women in the group. So I think C-sections are great. I encourage any women, or for that matter, men who are allies and interested in, especially ones that might be responsible for hiring and trying to figure out, well, gosh, I put out this job offer and the only people that applied were men. What do I do? How do I get more women to do it? Join SWE, talk to some of us. We've got lots of different suggestions to help folks that are trying to diversify their hiring pool.
Great. Well, Claire, thank you for the great conversation.
Absolutely. I'm really glad to share about both thermal interface materials and also women in engineering. They're both topics I'm passionate about.
Our guest today has been Claire Wemp of DuPont. For PCB Chat, this is Mike Buteau. Have a nice day.